Welcome to section 3.3 where we focus on the real zeros of polynomials. I do want to start with something that's not explicitly in the text as the fundamental theorem of algebra, but it's such a cool theorem that I just wanted to share it with you, and I think it ties a lot of what we'll be talking about together. I know it ties a lot of what we're talking about together. So in order to proceed, we do have to understand that when I say zeros, that I mean roots, I mean potentially an x-intercept if it's real, or I mean a solution. Those words are all synonymous with one another. So roots and zeros are the most common way that we will describe these. Now, I don't always want to say x-intercept because a root or a zero may be real or imaginary. And a real root is one that hits the x-axis. It's literally real, we can see it. And so that is the same thing as an x-intercept. An imaginary root does not, and we're going to get more into imaginary numbers later on this year, but for right now we're not focusing on those. But an imaginary root is not an x-intercept, and you can't see it. It's imaginary. All right, the fundamental theorem of algebra states that any polynomial that has a degree n has, counted with multiplicity, exactly n roots, or n zeros. So a polynomial that is degree 3, some cubic, has exactly 3 roots. Now, those 3 roots may be real or imaginary, depending. Now, imaginary roots come in pairs. So if we had a cubic polynomial and it had 3 total, it either has all 3 of those roots being real, or only one of them's real, because the other 2 have to come in a pair. They'd be imaginary, and it has a total of 3 roots. This is a really cool theorem because it tells us how many solutions or roots we need to actually be looking for based on the degree of our polynomial. Let's take a look at just these two polynomials here. They are functions, but we'll call them polynomials for now. This first f of x in white is a quartic trinomial. Down here in blue we have a cubic binomial. So the degree up here is 4 and the degree down here is 3. Let's take a look just at the f of x up top. We know that the degree, which we'll just call n, is 4. And so that means we're going to have a total of 4 roots. Now, we said imaginary roots come in pairs. So there might be all 4 real roots. They might all 4 be real. Well, if imaginary roots come in pairs, we might have 2 of them being real and the other 2 are imaginary. So we might only cross the x-axis twice instead. Only 2 of them are real. Or maybe none of them are real. Maybe none of them are real and all 4 of them are imaginary, because imaginary roots again come in pairs and pairs are an even amount. Okay, so there's 3 possibilities here. I'm going to look on Desmos and see which possibility we actually have. Okay, here is our function. There it is. I just want to be able to see what I wrote here. It does go down like kind of far. If we zoomed out just a bit, we could see that it has that little squiggle down there. But if we take a look here, it looks like we have 2 real roots. They each have a multiplicity of 1 because they cross straight through the x-axis, no squiggle, no bounce back. So here's one of the real roots. It looks like it's about negative 1.2. Here's the other real root. It's a positive 1.2. So it in fact was this one right here. This quartic polynomial is degree 4, therefore it has 4 total roots, and 2 of them ended up being real because we can literally see 2 of them, and they each have a multiplicity of 1, so that accounts for 2 of them. And then the other 2 are in fact imaginary, and we will not get there in this chapter, but we'll focus on that down the road. So here they are, 1 negative real and 1 positive real root. Okay, let's take a look at the second polynomial, this cubic binomial. We can see that this cubic binomial has a degree of 3. And that means it has, by the fundamental theorem of algebra, it has 3 roots. And imaginary roots come in pairs, so it might have all 3 of those roots being real and 0 of them are imaginary. Or it might have only 1 real and the other 2 of them might be the imaginary ones. Again, imaginary roots come in pairs. I realize IM is imaginary, so is IMAG. I don't know which one. You could use either one. But if we think about this, why can we not have two real roots? Well, that would mean that there's only one left to be imaginary, and imaginary roots have to come in pairs. All right, let's take a look on Desmos and see which situation this cubic is. Okay, I've graphed our polynomial, and we can clearly see that it's a cubic, and it has three real roots, right here, and right here. Remember, real roots are where we really cross the x-axis. They are the actual x-intercepts. So it ended up being this situation right here. All three of them are real. It looks like one of them is a negative number, one of them is 0, and one of them is a positive number. All of them are real numbers, and they each have a multiplicity of 1. So they each count for one of those three real roots. So that is the fundamental theorem of algebra. We will delve more into this and use this idea. We won't always need to graph something, but please know that you always can graph something in order to see the function and see the situation at hand.